This old book turned up recently when some stuff was being cleared out at the University of Canterbury. It contained what looked like a bunch of program listings, so they gave it to the computer science department, and I heard about it from some contacts that I have there. Nobody seemed to know what it was about. It sounded intriguing, so I asked if I could have a look, and they kindly let me borrow it. Let's see what's inside. It turned out to be full of assembly language for a machine that I didn't initially recognise. And there didn't appear to be much in the way of comments that would indicate what it was for. But there was a handy flowchart on the front. And as soon as I saw this heading, I knew what it was. When I was in my first year at Canterbury, students ran their programs on a system called CANTRAN. It was a batch system designed to run large numbers of small programs written in either Fortran or Pascal. When I was there, it ran on a PDP 1134. Although it had terminals, it wasn't really interactive. Essentially, you put in your program, the system compiled and ran it, and you got a printout at the other end. You could also tell it to store a program to run later, and there were ways to edit it, but it didn't have a screen editor like Vim or Emacs. Instead, you submitted a job with editing commands telling it to insert lines, delete lines, and so forth. There were a couple of other ways of entering jobs. In theory, you could punch your program on cards and feed it to a card reader, but I never knew anyone who did that. You could also write your program on coding forms and get the computer centre staff to enter it for you. I only did that once or twice before concluding that it took longer to edit all their mistakes out of it than to just type it in myself at a terminal. While we're here, let's check out the funky job line it used. The user was identified by a class name and a student number. You had a certain number of files to use, identified by numbers. A password was automatically generated and assigned to you, and you couldn't change it. The passwords all consisted of a 4-letter word and 2 digits. Almost all of the words were animal names, which made the passwords kind of cute and memorable. I did some Googling to see if I could find out any more about CANTRAN on the web. There's very little out there, but I did find this old page from the university's Chronicle about it running its millionth job in 1984, a couple of years after I used it. That's not very interesting in itself, but this paragraph reveals that the PDP-11 wasn't the first machine that CANTRAN ran on. It actually started its life on the university's first computer, an IBM System 360. All that's left of that machine now is its front panel, which is on display in the foyer of the computer centre as a museum exhibit. At least it was a few years ago. Whether it's still there now, I'm not sure. I couldn't find any pictures of Canterbury's actual machine, but this is the kind of thing we're talking about. I've no doubt it came with a perfectly capable Fortran compiler. But compiling a Fortran program with a full production quality compiler would have been a fairly heavyweight operation in those days. And it likely wouldn't have been able to handle the load of hundreds of tiny programs going through it every day. Also, it might have needed some obscure job control statements that would have been rather intimidating to a beginner. So I can understand them wanting something simpler. Getting back to the Green Book, it's clear that this is an early version of CANTRAN written in System 360 assembly language. Now, I don't know about anybody else, but I think this is an important piece of the University of Canterbury's computing history that should be preserved. And not just as a dusty old book sitting on a shelf. What I'm planning to do is scan the pages, convert them to machine-readable form, assemble it and get it running on an emulator. If all goes well, I'd like to make it available on a website where anyone can go and experience a little of what it was like to be a computer science student at the University of Canterbury in 1959. Before going any further, I'd just like to say that this project is not endorsed or supported by Canterbury University in any way. It's just my personal project. So, how to make this dream a reality? Well, first I obviously need to be able to scan the pages. Fortunately, my scanner's image area is just big enough to capture all the important parts of the page if I line it up carefully. I just scanned one page to begin with for testing purposes. The raw scan didn't have much in the way of contrast, so I played around with it a bit in preview to see if I could make it better. There wasn't much room for adjustment. This was about as good as I could get it. The next thing I did was go looking for OCR software, and that led me down a series of rabbit holes. I wanted something I could call from Python, and I found a few candidates. One was called Easy OCR, which sounded good. I'd rather have that than difficult OCR. From the tutorial, it did indeed seem to be quite easy to use, and looked like it would give me the data I wanted. The process of trying to get Easy OCR running looked something like this. Pip couldn't find a binary of the Python interface for my platform, so it tried to compile it, which didn't work. So I downloaded the source to see if I could fix the problem. I went round this loop a few times, until I found an issue that a developer had decided to resolve by telling people to use Clang 9 or later. I had Clang 8.1.0. So I tracked down a binary of a 9-point-something version of Clang for my system and installed it. With that, I was able to successfully compile and install the Python module for Easy OCR. All that was left was to try running it. So I knocked together a quick test program and gave it a shot. Yeah, it tries to use instructions that my CPU doesn't have. Supposedly there's some way to compile it so it doesn't do that, but I couldn't get that to work. So I decided Easy OCR was too hard and started looking for something else. I found one called Tesseract, which also has a Python interface. My efforts to install it started out much the same way. I found I needed an even newer C++ compiler. This time I decided to go straight for the latest version I could find for my system, which turned out to be Clang 15. Using that I managed to get a successful compilation. But when I tried to run it I got an error from the dynamic linker about an invalid linking command. After pondering this for a bit, I figured what was going on was that my dynamic linker was too old to fully understand the libraries that came with Clang 15. This was a bit of a problem because the dynamic linker is part of Mac OS X, and I didn't like the idea of trying to upgrade it in case it broke my whole system. So I thought, well, maybe I could transplant the libraries that came with Clang 9, which worked, into my Clang 15 installation. I decided to test this idea by replacing one library, the one I'd got the error message about, and see what happened. If it was able to link that library okay, I'd go on and replace the rest. To my surprise, not only did that library work, everything worked. Apparently it was just that one library that was the problem. I gave it the Hello World test and that seemed to go fine. So then I tried it on the page I scanned earlier. That seemed to go okay too, at least at first sight, but how accurate was it? I compared the results with the image and this is what I found. It missed quite a lot of the top line. It got most of the words in the left column but made quite a few errors. I gave up doing a detailed error analysis in the orange areas. It found most of the characters, but there was about a 25% error rate. This is not a criticism of Tesseract. I'm sure it works very well on a nice clear high contrast image, but I just don't have that. And for my purposes this isn't going to be good enough. I'm going to need it near 100% accuracy if this project is to have any chance of success. At this point I stopped looking for off-the-shelf software and started thinking about writing something myself. I didn't need a general purpose OCR system. My problem was quite constrained. There was only one font with no lowercase letters, all the characters were the same size and they were arranged on a regular grid. It shouldn't really be all that difficult. I wrote some Python code to load up an image and started playing around with it. The first problem I faced was the image was a bit skewed. I needed to find a way to straighten it up. I considered various ways of figuring out the angle I needed to rotate it by. At first I was thinking about scanning from the left edge to find out where the characters began at the top and bottom and using the difference to find out the skew angle. But the lines don't necessarily all start in the same column, the heading at the top of this page being an example. So I'd have to somehow identify and ignore lines like that. The more I thought about it, the more it seemed like it would all be rather complicated and prone to failure. I needed a different approach, and here's what I came up with. It essentially amounts to calculating one frequency component of a 1D Fourier transform along each scan line. If that doesn't mean anything to you, don't worry, I'm about to explain. First, you take a sine wave with a period equal to the expected width of a character, multiply all the pixels along a row by it, and add up the results. That gives you one component of a vector. Then you do the same thing with another sine wave shifted by a quarter cycle. That gives you the other component. What this does is detect periodic features with a period that matches the period of the sine waves. The magnitude of the vector is a kind of signal strength indicator, telling you how strongly it detected such features. The phase angle of the vector depends on the position of the detected features in relation to the sine waves. Here's what that looks like. The horizontal red lines represent the signal strength for each row. The vertical red line is the threshold. I'm ignoring any row with the signal strength below that. I've put a blue mark at a horizontal position that depends on the phase angle. The absolute position of the blue marks is arbitrary. To best show what's going on, I've manually shifted them so that most of the marks fall between characters. This works surprisingly well. You can see that the blue marks track the positions of the characters quite closely as they go down the page. But if we zoom out a bit, things start to go wonky. The marks start to jump around, and eventually they all shift over by one character. This is happening because angles wrap around. To calculate the angle from the vector's x and y components, I'm using the atan2 function, which returns a value between pi and minus pi. Although the angle is only changing by a small amount from one row to the next, if it goes past the half-turn mark, it suddenly jumps from pi to minus pi or vice versa. This causes the blue mark to shift by one character width. To solve this problem, I keep track of the phase of the previous row, and if it changes by a large amount, I add or subtract 2 pi to get it back on track. This results in the blue marks tracking the characters nicely all the way down the page. The final step is to fit a line to the blue marks and find its angle from the vertical. That's the amount I need to rotate the page by. And hey presto, a perfectly upright page. The next thing I wanted to do was improve the contrast. I found the darkest and lightest pixels in the image and scaled the brightness of all the pixels so that they filled the full range from black to white. This didn't work all that well because the lighting conditions weren't uniform across the page. I think there must have been some bleed through from text on the pages below. So then I tried dividing the page into small blocks and doing the same thing separately for each block. That worked a lot better. Next I needed to find the origin of the character grid. To do this I temporarily applied a threshold to produce a 1-bit image and then went looking for the topmost and leftmost black pixels. I couldn't just do this for the whole image though, because there was some noise near the edges of the page that would have given spurious results. This was my first attempt at dealing with that problem. I found the position of the first black pixel in each row and column, shown here in blue, and took the median of them, shown in red, to remove outliers. That worked okay for the left margin in this example, but not for the top margin, because there were too few characters in the top line and they all got rejected as outliers. To fix that, I divided the width and height of the page into bands and found the median of each band. Then I took the minimum of all those. This worked quite well and gave me a good estimate of the left and top margins, shown here by the thick blue lines. And here's the grid, aligned with the margins and overlaid on the image. The next thing was to iterate over the grid and extract the characters. This was complicated a bit by the characters being a bit higgledy-piggledy and not always lying entirely within their cells. So I had to chop out an area a bit bigger than the cell to make sure I got the whole character. Then I found the edges of the character by looking for the outermost columns containing a dark pixel, where dark is defined as being below a certain threshold. For later steps I'll want all the character images to be the same size, so I trim the image down to that size with the character centered in it. I also trim it vertically the same way, giving this final result. This worked well for some characters, but often the initial cell grab would pick up a bit of a character from an adjacent cell, which caused the trimming to go wrong. I fixed that by first looking for rows and columns with no dark pixels, and then looking past there for dark pixels. This gave a much better result. Here I've drawn each character back on top of the cell that it was extracted from. It looks like it's done a reasonably good job of lining the characters up. But taking another look at these two E's, while the first one gets trimmed very accurately, the second one comes out a little too low. A close look reveals why. The top red trimming line is getting caught up on the black blob in the top left corner. To fix that, I need to disregard what I've already trimmed off to left and right when working out how much to trim off the top and bottom. That looks better. It was time to start to try recognizing characters, and for that I needed a set of example character images to compare things against. I arranged things so that I could click on a character and type a key to save it as a small image file. Then I put them into my image editor and made a tile map that I could load in. To recognize a character, I went through all the reference images, finding the mean square error between the character image and the reference image, and picked the smallest one. This is the code which does that. The images are all in NumPy arrays at this point, which makes the calculation quite easy. Here it is showing the characters it thinks it found. It got most of them right, but it mistook an L for an E, an I for a 7 and an O for a U. We'll have to do better than that somehow. Seeing as proper alignment of the images to be matched seemed to be quite important, I tried matching multiple times against the reference image offset by 1 pixel in every direction. That seemed to help. It got most of the top line right now, but it still had severe problems distinguishing between zeros and Ds. I found a better example of a D to use as a reference image, and that seemed to help, although it didn't eliminate the problem entirely. Looking at the characters I got wrong, I noticed there were places like this where different parts of the character have different amounts of contrast, because the character straddles 2 of the blocks I used for contrast enhancement. That made me think that once I've located the grid, I should redo the contrast enhancement pass using the character cells as the blocks. That way the whole of each character will get its contrast adjusted by the same amount. Here's what that looks like. The characters are much more uniform now. It's mostly stopped mistaking zeros for Ds, but it does mistake them for other things sometimes, and it occasionally thinks a D is an O. Looking at this D here, you can sort of see why. The top left corner is printed a bit faintly, and since the corners are the main thing distinguishing D from O in this font, that's a problem. I was kind of out of ideas at this point, but then I had a thought. Remember I said earlier that I expected Tesseract would work better with a higher contrast image? Well, I've got a higher contrast image here, so why not try feeding it into Tesseract and see what happens? This is what happened. It worked quite well. It got that big block of zeros perfectly, which was more than I was able to do. I found 15 errors out of around 600 or 700 characters, which is near a rate of about 2%. There were a few places where it reported a lowercase letter instead of the corresponding uppercase one, but that's easily corrected, so I didn't count those as errors. Although it does seem to be able to tell O's from D's fairly reliably, it is confusing O's and zeros. I think that where it gets them right it's because it knows that letters tend to go together and digits tend to go together, but that sends it astray in the middle here where we have hex numbers. This is a bit frustrating because the O's and zeros are clearly different. The O's are square and the zeros are round, but I don't have any way of telling it that. I played around with tweaking some parameters to Tesseract to see if I could improve anything. There are 3 sets of training data available for it, an old legacy one, a fast one and a best one. I ended up using the best one since it wasn't much slower than the fast one and seemed to produce the best results overall. I also settled on passing these parameters to it. PSM11 tells it not to bother trying to find blocks of text on the page, since I'm only interested in individual characters. The others tell it not to use any dictionaries to try to recognize words. That would be counterproductive, since my text isn't made up of English words and I don't want it auto-correcting anything. I also tried using higher resolution scans, The one I've been using so far was 150 dpi. This one is 300 dpi. It didn't seem to make much difference. This one is 600 dpi. The accuracy is actually going down and starting to make mistakes in the top row now, which it wasn't doing before. At this point I concluded the test rank was both too smart and not smart enough for what I was trying to do. I decided to give my DIY approach another go on the 600 dpi image. I did a lot of experimenting. I won't go into the details, I'll just give a summary of what I came up with. First I increase the contrast of the character and then I blur it slightly, which makes the dark areas a bit more uniform. Then I increase the exposure a bit more, which washes out the noise in the background. Then I quantize the image to 4 levels, and finally replace anything that isn't white with black to give a 1-bit image. This is what I compare with a set of example images to find the closest match. I tried it with just 3 characters to begin with, to see whether it could distinguish between O's, zeros and D's, which is something I was having a lot of trouble with before. It did extremely well. Having the extra resolution seemed to be helping a lot. So I pressed on and saved models for the rest of the characters on the page. One change I made was that instead of assembling all the models into one image, I just load them separately from individual files. Not only does that require less work, it lets me have multiple models for the same character, for example these 2 bees here. Hopefully this will make it easier for it to recognize characters that aren't printed perfectly. I also created a reference file containing a correct version of all the text on the page, so that I can automatically calculate an error rate. I managed to get it down to 0.36%, which is by far the best result I got up until then. A lot of the mistakes were in the top line, which was a bit fuzzy because the paper wasn't pressed against the glass properly. So I'm going to mostly ignore those. I got confused by this D with spots of dirt on it. It mistook some E's for F's because they were very faintly printed at the bottom. It also missed a few zeros, not sure what was going on there. Rather than chase that down further, I wanted to try some other things. I wasn't sure whether turning everything into 1-bit images was the best thing to do. So I did another series of tests where I overexposed the whites and underexposed the blacks and left everything in between as a grayscale. I also matched each character with a shift of up to 2 pixels in every direction for a total of 25 matching positions. After tweaking various settings, I got the error rate down to 0.05%. There were only 3 errors on the whole page. One of them was this particularly faded E on the top line. The others were these 2 E's with the faint bottoms again. These are really hard to fix because the bottom strokes are barely darker than the background noise. If I adjusted things so that it could match them correctly, it would then start mistaking some of the F's for E's. So I concluded that was about the best I could do using this approach. But before stopping there, I wanted to try one more idea. Something in between a 1-bit image and a full grayscale. This is what I tried. I quantized the image to 8 levels, threw away the top and bottom 2, expanded the rest and re-quantized it to 5 levels. Here's what that looks like for a few characters. This is one of those difficult E's, and it seems to have made the bottom stroke a bit darker. But the best thing is the final result. It handles both of the difficult E's no trouble at all. We're down to just 1 error on the whole page. And guess what? It's our old friend the faded E on the top line, which I'm really not worried about at all. So I think we have a winner. The next step will be to scan another page and see if it still works as well. But I think that's enough for this video, so I'll see you next time.